I think you may be muted. I don't know if it's just me.
How about now?
Sounds good.
Great, thanks. If you guys are present, please type in present. Um, all right, as far as administrative stuff, I updated all the sections in the course schedule to specific textbook sections. It gets a little loose near the end because I'm getting through stuff a little more quickly. Like, for example, I only had one lecture in multimedia. Um, Let's see. Course evaluations. We are almost there, guys. We're at 41%. We need 50. If you haven't done it, please do. I'll send another reminder on D2L, but we are almost there. Um, Anything else that you guys want to discuss? Cool. Exciting. We're almost at the end. All right. Um, so, yeah, let's get into it. All right. So today we'll talk about network support for multimedia. I don't know if you guys can hear this, but the cool quote is, it's a triumph equaled only to its monumental failure, which basically describes quality of service support in networks. And so today we'll find out why it's so hard to provide adequate bandwidth or adequate delay to multimedia traffic or different types of traffic. Um, and even though all the mechanisms I present, they sort of don't work, and I'll explain why. It's still really important to know them because they do work sometimes. And more importantly, if you ever run into these problems, um, if you think you can design a better mechanism, probably you can't. It's probably a fool's errand. So be very, very careful, when you talk about providing priorities to certain types of traffic or guaranteeing certain level of service. So that's really what this lecture is about. It's a sort of a cautionary tale. All right, so we can look at the ability of the network to guarantee certain levels of service. Okay? And what we have in the internet or in the networks we discussed thus far is basically what's called best effort or best effort service. And the idea there is that all traffic is treated equally. There are no special packets. It's just all IP packets with the same priority. There's no guarantee on delivery, delay, on really anything. There is no network support. The network is not aware of what traffic it's forwarding, but it is not complex. And in fact, it's deployed everywhere. So this is the current state of what gets done. Now, there were two different ideas on how to provide network support for different types of traffic. Those were called differentiated services and integrated services. So diffserv and per connection QoS or integrated services or INTSERV. INTSERV was actually the first proposal. And the idea was coming out of telephone networks, of course, where you have some per connection guarantees. Okay? They would be soft or hard depending on the design or the network or the type of traffic after the flow is admitted. So no new flows could enter the network unless the network could guarantee that there was enough capacity for it and there were enough resources allocated along the path to cater to a particular traffic. There were packet markers, scheduling, policing, and mission control, quite a few mechanisms to make this all work together. It ended up being quite complex, and basically no one wanted to use it. So the next proposal after the failure of this kind of first perfect matrix was to propose differentiated services where instead of guaranteeing network performance on per connection basis or per flow basis, The guarantees were provided based on traffic classes, and those were sort of soft guarantees. They weren't quite as hard. You wouldn't guarantee latency below a certain number value or at least some level of throughput. Okay? And this was done through a similar set of mechanisms, but without admission control. So basically, you would try to get data into the network and then just treat certain classes of traffic differently. It has medium complexity and some deployments. I'll kind of get into it where it is useful. Okay. So the biggest question in this lecture is why aren't integrated services or differentiated services more widely deployed? Okay? And there's a number of reasons for it. The first is the cost of complexity. Right? Deploying mechanisms that can differentiate traffic in the network, meaning at all the routers, just means that routers become more complex, which means they become slower because they have to do more stuff with each packet. They need to figure out what class it belongs to. They need to, maybe put it in different queues, treat it differently. There's just a lot more processing, which, as we know from our discussion of routers, we want to do as little processing as possible in the routers to keep everything in hardware, all the forwarding in hardware. Okay? Even if you could solve these issues of complexity with mechanisms and more computation power, perhaps you could, there's still difficulties in negotiating what different classes of service mean across ISPs. You could standardize those. For example, this is the class of service for video. This is a class of service for gaming, for, voice, right? You could come up with these few classes. But that does complicate peering agreements where, okay, maybe I'm sending more voice traffic for you, but you're sending more video traffic for me, and it just complicates these contracts. And the problem that ultimately ends up happening is that there's still no guarantee on those services. So back in the day when people were playing with this idea, you could buy different levels of internet. You could buy gold service or silver service or then platinum service. And eventually everyone ended up buying platinum service just because there wasn't enough, or gold service rather, because there was there was such scarce network resources that people just paid up. And so you ended up with a lot of people in the gold service anyway, meaning that you basically had one class of service for everybody. And so there was no more differentiation. So for these kind of three reasons, networks don't really want to deploy these things because there's no advantage to it, and it just brings complexity, and everything eventually collapses into gold service anyway. There are also kind of bigger systemic reasons why quality of service or differentiation of traffic isn't really useful. So let's say that you have plenty of capacity in the network, right? There's more capacity than the amount of traffic that users can send. Well, in that case, it doesn't matter whether or not you differentiate that service or not, because all the traffic goes through anyway at the same speed, which is really quickly because there's just not that much traffic compared to the capacity of the network, right? You can think of it as, you have a normal car on a highway and an ambulance on the highway, and the ambulance is supposed to have higher priority, but there's no one else on the highway, right? So the car can travel just as fast as the ambulance. There's no reason really to differentiate the two. On the other hand, when your resources are severely constrained, right, and you have a highway that's basically just full of ambulances, well, they kind of have the same problem. There's just not enough capacity. So even though, they have the high priority, they're still going to be in congestion, right? So quality of service really just works kind of in this happy middle, and networks tend to be either full of capacity or full of congestion. There's not a lot of happy middle type things. And as an operator, you basically want to keep it in the plenty of capacity space. It's also faster and cheaper to have a dumb core, meaning simple routers. They happen to be faster, which makes it easier for you to live in the high capacity regime. And then ultimately, application mechanisms can do some adjustments for lack of bandwidth, for example, by reducing video rate. Okay, so kind of a complex ecosystem of reasons, but there are some areas where differentiated service do see tractions, which would be in cellular networks. Does anyone have an idea why? Why would cellular networks actually care about differentiating traffic? Mhm. And given all these reasons, it's really kind of not clear. But cellular networks actually do live in sort of a medium where there's not quite enough capacity often, and there is a lot of real-time traffic, for example, for voice data. So you do have these incentives for making sure that voice calls don't get dropped. So we do need to prioritize them. And often deploying extra capacity is quite expensive. So they aren't really congested, but they don't really have so much capacity that where QoS, quality of service mechanisms, are not applicable. And so when we get to 5G, you'll see, or we actually talked about it already, that there are network slices where you can have different applications basically live in a different virtual network. And then you can guarantee quality of service, not for individual flows or classes of service, but really for individual network deployments, which might serve a particular client or a particular application. Okay, so with that kind of convoluted intro, let's look at what these mechanisms, how these mechanisms are built, or what are the principles behind them. So the idea we'll discuss is differentiated services where there are multiple classes of service. So we'll move away from the one size fits all service model and have multiple classes of service where they are treated differently. And you see situations where this is applied in real life. For example, people trying to get into the club, you have a VIP lane and you have the chump lane. So the high priority packets go through in the fast lane and all the low priority packets are kind of queued up, right? Until there's enough capacity for them to get in. And so we do see these mechanisms where there is sort of some capacity, but it still makes sense to not let everybody in at once. You want to kind of queue them before they're able to be admitted. Right? And so here we have not in quality of service, not on individual basis, but based on classes of service. And in the IP packet, you can see there is this type of service field which can be used to mark packets as belonging to one type of class of service or another. Okay. Let's look at some of the problems that arise in a network. So we have two flows here. We have a 1.5 megabits per second link between two routers that is shared by two flows. One is a voice flow between host 1 and host 3, and one is an HTTP flow of data, from a web page traveling to a requesting host 4 from host 2. Okay. So if I tell you that we have 1.5 megabits per second link and voice uses 1.5 megabits per second, or maybe, I guess it's not just a voice, but it may be a video call as well. And then the HTTP traffic is 0.5 megabits per second. What is the problem? There seems to be enough capacity, but I'm telling you that there is a problem. What is the problem?
Well, one service is going to get all of that bandwidth and the other is just going to get ignored.
But what if they actually are sending at 1 megabit per second and 0.5 megabits per second?
Oh, yeah.
It seems they might fit. But what we know is that HTTP traffic uses TCP, right? Which is going to expand into available bandwidth. And so if there's a request for a lot of data on that web page, TCP is not going to constrain itself to this. So in fact, I lied. It's not going to stay true to this requirement that it limit its sending rate, right? Or it could be bursty. this could be an average rate based on how often the person requests any page, but momentarily the sending rate could be quite higher for this average to be at 0.5. Okay. And so we can create a congestion where there's so much HTTP data that this queue fills up, and so there's some packets for H1 might start getting dropped because there's no space for them at this router. Okay. So we want to differentiate or have a way for this router to look at what's in its queue and say, okay, this is voice traffic, this is HTTP traffic, I can delay HTTP traffic. Okay. So to do this, we need to mark the packets. Somehow, there needs to be a differentiation of the packets, and so the packets need to be marked, as I mentioned, in the type of service field in the IP packet. And then through policing, this router can force the adherence to a certain forwarding policy, for example, that the voice traffic is only forwarded at 1 megabit per second, and that the HTTP traffic is only forwarded at 0.5 megabits per second. Okay? So it needs to have marked packets, and it also needs to maintain, this router also needs to maintain some metrics on how much data it is forwarding for each flow. Okay? So the question then is, where should these packets be marked as belonging to one flow or another? At the routers or at the end hosts? Well, if we do it at the end hosts, then they can basically lie about it. Right? The HTTP server can say, yeah, I'm sending voice traffic. I should have high priority here, but it shouldn't, in fact. So the first hop router is usually tasked, or in these types of mechanisms, with marking the packets. And that provides isolation between the classes. Okay. So let's say that we can mark these packets. They're arriving at this router, and the router says, okay, great. I got my voice packets, I got my HTTP packets, and I'm going to enforce that they're forwarded at some rate. So I'm going to forward the HTTP packets at 0.5 and voice packets at 1 megabit per second, and that's what I'm going to do. What is the problem with this? Why is this bad design? Any thoughts?
I'm fairly sure that it's not.
You're not sure that it's not. Okay, great. Well, what if the voice traffic doesn't actually have any packets to send? Right?
Yeah.
Let's say someone is quiet. There's a lot of pauses in the conversation. And then those pauses could actually be used by HTTP traffic because there is extra capacity in this network. So the sort of hard assignment of bandwidth to each flow ends up being wasteful when the flows aren't sending data.
Of course.
Mm-hmm. Yeah. So even though we want to provide isolation between flows, we still want the available resources to be redistributed or shared as efficiently as possible. Okay? And this isn't so much used anymore. I haven't seen much of it, but for a while, cable companies were advertising something called Network Boost, where you would basically be able to send more data than what was kind of guaranteed to you or what your contract is for, right? So if you have a contract for 40 megabits per second, sometimes you could send up to 100. And this basically meant that if no one else was using the network, your router would allow more data to be sent into the cable network. Okay. So there are these two types of mechanisms. One is scheduling and one is policing. Okay, so scheduling is, can I click on this? All right, can't click on it, but it's basically a scene from what is this movie? Old School, where the main character says, "Oh, I need to go to Home Depot. I need to go to Bed Bath and Beyond, and like, I don't know if I can do it. I don't know if I'll have enough time." Right? And so scheduling is about finding the time for all the different packets, okay, or which packet to send next. And then policing is the constraining of oversending. So I put this picture up. There's limiting the number of demons. This came out of a class. This is before the new Doom came out, so everyone was talking about it. I thought this would be a great image. Anyway, there are these two mechanisms. So the first one is the first mechanism we want to talk about is scheduling. And there are different mechanisms for this. For example, first in, first out, where we would send something in the order of arrival. So you have people queuing up for the bus, as apparently they do in England. They're waiting at the stop, and then you would, whoever's first is the first person to get on the bus, first in, first out, great. And then you have some discard policy if the queue ends up being too long, right? Or if there's no room on the bus, right? That not everybody can make it. So the general model is that you have some arrival of packets, some arrival rate. You have a queue, which is the waiting area. And then you have some departure rate, or what's also called the serving rate. Okay? So at some rate, packets are arriving into this queue. At some rate, they are being removed from this queue. And hopefully this queue doesn't become full, because then you can't admit new packets. Okay? So let's look at a real world scenario. You have these nice old people, mostly old ladies, lined up for the bus. The bus arrives. There is limited room. Not everyone can get on. What is your policy for deciding who gets on the bus and who doesn't get on the bus?
Typically, first in, first out would be
first in, first out. So you take the first five ladies and let them get on the bus.
Yeah.
All right. Is that fair?
Seems fair enough. I mean, they've been waiting the longest, supposedly.
Well, what if some of the people in the back of the queue are older?
Well, then maybe they won't have to make the next bus out.
you can create these different scenarios where fairness is one thing. You can think of equity as another, right? But there could be different objectives for you as the operator, right? Where you want certain packets to get on and certain to not get on. Yeah, Michael.
As my old scoutmaster used to say, fairs are places where pigs go to win blue ribbons. So
fair is what? Say it again. I think you're breaking up. I couldn't hear what you said, Michael.
I think you said the fair is where pigs go to win blue ribbons.
Oh. Yep. There's some truth to that. All right.
So not fair.
You could start implementing different policies. Okay. So for example, you could say, well, the queue can only get so long, right? Where new packets arrive, you just don't let them to the queue. You only let the queue be equal to some capacity or some serving rate. Okay. You could have priority, for example, based on age. Or you could also pick a random set of people from the bus, from the queue. Okay? Or if the queue is too long and someone arrives, you could pick a random person to drop. You could, do all kinds of things to provide some higher level objective for your network. Okay. So one way of doing this, let's say you had some priority queues where you wanted to, let's say, I don't know, have people over 65 get on the bus first. All right, so you could put them into two different queues. You have the high priority queue and you have a low priority queue. All right, so you would have a person at the bus stop, kind of checking people's age, and then depending on how old they were, they would go into one queue over the other. And then when you have the ability to serve from the queues, when a new bus arrives, you would take as many people as you could from the high priority queue. And if there was no one left in the high priority queue, then you would start taking people from the low priority queue. Okay? So that would guarantee that everybody with high priority would get on the bus over anybody with lower priority. So there's these two mechanisms. One is the marking of packets to classify them into each queue. And then there's some serving discipline from the queues where you pick, in strict priority, anybody from high priority area before anybody from low priority area. Okay? This gets a little trickier there's some kind of corner cases when you look at the arrival and departure of packets from queues in a network. So let's say that you have a high priority packet arrive, and then you transmit that packet, and then it departs. Okay? What happens if you have these two other packets arrive while you're transmitting the first packet? Okay? Well, under strict priority, packet 3 should be served first, and then packet 2, right? Because we want all the high priority to be transmitted first. But if packet 2 is already being served, we will not interrupt the packet, we'll finish sending it, and then packet 4 would have to wait until the next opportunity. So you only make a decision when you're trying to pick a next packet, you're not preempting packets. Right? And then if there's no one in queue and you have a low priority packet, you can just transmit it right away. Okay. Then we can make this a bit more flexible and have multiple priority packets, multiple priority classes, and a round-robin mechanism where we are serving packets from high priority queue, medium priority queue, and low priority queue according to some weight. So it's not a strict priority, it's weighted for queuing. So in this mechanism, every class of packets gets some weight. So for example, the weights here could be 3, 2, and 1. Okay? So we would serve up to 3 packets from high priority queue, then up to 2 packets from medium priority queue, and then up to 1 packet from low priority queue before going back to the high priority queue. You're basically setting forwarding ratios from these queues. Now, if there is no one in high priority queue, you would just move on to medium priority queue and then low priority queue and then restart, seeing if anyone arrived in the high priority queue. Right? So your serving rate is basically your ratio of serving rate is the weight of your class compared to the sum of all the weights of all the classes. And the work conserving discipline is that you move on from one class to another if there's nothing to send, for example, in the high priority queue. Okay. So then we move to policing, which is how much data can be sent in the network, right? Not just who gets to go if there is capacity, but actually how do we restrict the forwarding rate of a particular flow, right? The two mechanisms go hand in hand. One picks the priority, the other one picks kind of the volume of a link. Okay? To do this, though, this gets a little trickier because if we want to limit the traffic to not exceed some rate, there's a question of what do we mean by rates in terms of over a given time period. Right? So we can look at an average rate where we don't want the flow to send more than some number of packets per some unit of time. Okay, like 10 packets per second or 1 megabit per second of data. Okay? But the question is, what is the interval? We can define it based on a second, okay, which is 100 packets per second, or we can define it on per minute. But if you define on per minute basis and you try to send 600 packets per second, well, that's actually going to be higher than the 100 packets per second if you averaged over a second. Right? So the larger the interval, the larger becomes the possibility of this large burst or peak rate. Okay? So you might want to limit the sending rate to some average as subject to the fact that we never exceed some peak rate in a much smaller time interval. Okay? Or you can say that there's some burst size where only some number of packets can be sent back to back, and then you have to go, back to limiting the average rate. So let's see how this could be implemented. The basic mechanism for this is the token bucket, which can be modeled as follows. You have some packets that are being sent. Okay, those would go to a queue. Okay, and then you have this bucket of tokens, a virtual one, obviously, where you have tokens being generated at some rate. Let's say R tokens per second. They just kind of drop into this bucket. And then the bucket can hold up to B tokens before they start overflowing. So you can't ever collect more than B tokens, even if you wait long enough for them to be generated. Okay? So now for the packet to be sent into the network, it can be taken out of this waiting queue only if it can be paired with a token that's in here, and then the packet gets forwarded. So this is just a kind of a virtual check if a packet, if there is a token for a particular packet. Okay? So what this does is that if there's a constant large flow of packets in here, they can't ever be forwarded to the network faster than R tokens per second. Right? Because initially, even if this bucket is full, you go through the B tokens pretty quickly, and then eventually you just have one token arriving, and then that one token gets paired with the next packet, and then the packet gets forwarded. But this mechanism also allows for a particular burst. So if, let's say, these packets arriving intermittently, and you have, let's say, 5 packets arriving, and then you have more than 5 tokens being queued, those 5 packets can be sent right away. And so if your packet is intermittent, it can still achieve this R tokens per second rate given some bursts. So on average, you can't exceed R tokens per second, but if you just did the tokens without a bucket, your rate would be lower, because if you don't have a packet here, you can't forward it, and so you're kind of losing the aggregate average rate unless you're able to queue up some tokens to handle a burst. Does that make sense? Does anyone have questions?
So it kind of acts as a capacitor, more or less.
Pretty much. Okay. So how many packets can enter the network during the interval, some interval t? How would you write up that formula? I know you guys love formulas. Going once.
Would it be RT plus B?
Yes, exactly right. So during some time, you can basically get R tokens, and then it's also possible that you had B tokens already being queued up in there, in the bucket. All right, great. Easy enough. So, question for you guys. This will require drawing on your part. Design a token bucket pulsing mechanism that limits average rate to V packets and peak rate to P packets in some interval T. So average rate V and peak rate P. So I'm looking here for a drawing of a something that looks like this, and then you guys have to decide kind of what this drawing looks like, and what are the sort of parameters in this drawing governing token generation and storage. All right. This is what I have. All right, let's see how this works. All right, so we have some set of incoming packets, and then we're going to first limit the average rate, and then we'll limit the peak rate. All right, so we have to do it in two separate tokens. So here we have tokens arriving at R tokens per second and up to B tokens, but how does it have to do with V? Well, if the sending rate is R times T plus B in some interval T, okay, we want that value to be less than or equal to V. Right? So you can kind of tune your parameters here versus based on how bursty your traffic is. If your traffic is more bursty, you would want a larger B, okay? Whereas if your traffic is less bursty, you would want a larger R to get as close as possible to V. Okay? So the problem with this approach is that, as far as peak rate, is that you can end up with a large burst, right? And a burst is going to be potentially over the peak rate, right? Because it's just back-to-back packets. So to limit the peak rate, you have another queue that generates P tokens per second, okay, but up to 1 token. So those are generated quickly. And basically, if you have a lot of packets here, they're going to be delayed to P tokens per second. If you don't have any packets here, then there's no reason to queue up tokens in this bucket because we don't want to have any burst out of this that's faster than P. Okay, so why not limit B to 1 here? Right? You could have this be very small, but then if your traffic is bursty, you would actually go under V, right? If you're not sending incoming packets at rate R, you would go under V without having some ability to burst or to catch up, right? The burst basically allows you to catch up if you haven't been sending, right? And then if you make B large, well, then necessarily you would need to constrain R, which is not good for traffic that's sending at a fairly steady rate. All right. So then with those two mechanisms, which is classifying packets into multiple classes of service and having a token bucket mechanism, you can actually provide upper bounds on delay in your network. Okay? So if we look at this scenario, okay, and we just want to guarantee some delay on this router for the high priority traffic, right? Maybe we want to limit this the wait in this queue to like 10 milliseconds, and then we know that there are 3 routers along the way. Okay, so we know that the maximum delay that packet can be subjected to in queues would be 30 milliseconds, and then I don't know. We know the total propagation delay would be 5 milliseconds, right? So we know that the packet cannot be delayed in the network more than 35 milliseconds. And that's generally how this works. So propagation delay is pretty much constant, right? Once your packet starts sending, it's just sending at the rate R in this case on the link. So we just need to end up the queuing delay at all the routers. And to that, we want to kind of bound the maximum queuing delay that can occur at a router to do that, right? Okay. So you can ask yourself, what is the maximum forwarding rate of out of this Q1 on this router? Okay. And it's basically going to be the transmission rate on the link R multiplied by the proportion of that rate that is given to this queue. Right? So if both queues are full, this is going to be your rate. If there's nothing in Q2, well, then this rate is going to be faster, but you know it's never going to be slower than W1 over the sum of all the W's times R. Okay, so now we know how fast we can serve data out of this queue. Great. Okay. So then we can ask, okay, what is the maximum queuing delay of packets in this queue? Right? If we have this mechanism in front, okay, where tokens are generated at rate R1 and we can accumulate up to P tokens. Okay. So basically, the maximum delay is the amount of packets you can burst into this queue, right? Because the burst, let's say, is 4, so you end up with 4 packets in this queue, and now you have your delay is how long it takes for this packet to get to the front of the queue and be transmitted, and that depends on how quickly you can clear this queue, and the speed at which you can clear this queue is the forwarding rate of the link times the weight of the queue, right? So B, of course, is not in the number of packets in this equation, but in the size of the packets, but we're simplifying this. So you have some serving rate out of this queue, and then that serving rate, you divide the amount of data in this queue by the serving rate to get the wait time in the queue. And the maximum size of this queue ends up being bursts, right? As long as the forwarding rate out of the queue is faster than R1, obviously, right? Otherwise, it's going to grow. Okay, which gets me to my last question, which is what happens if R1, the token generation rate, is greater than the serving rate out of this queue, right? And that basically means that you can have packets arriving into this queue faster than they can be served, which means that the length of this queue is going to perpetually grow, which means that's something that shouldn't be allowed, right? That just means your packets are going to start getting blocked. So when you are if you have a mechanism that does admission control, meaning that, hey, we want to add a new high priority flow in this network, Network says, okay, great, I need to change the parameters at each of the routers to serve that amount of traffic, meaning I need to up R. The question that the router should ask is, can I up R in a way that I still have enough forwarding capacity out of this queue so that this queue doesn't grow infinitely long? Okay? So that's admission control. You get a flow, you say you want to guarantee the delay on end-to-end basis. You say, okay, cool. I need to then look at all the routers saying, hey, can we add so much flow rate into the high priority queue? Okay, maybe you can check R against the serving rate. Okay, you end up upping up R on all the links, and then you say, okay, now the network is ready to admit this new flow. And obviously, there would be a lot of signaling involved in guaranteeing that. But this is still, you might not deploy this in the network, but that is something that could be quite useful to you if you're building a distributed application with, requests flowing between pub subs, between queues, between different processes. You're building a basically microservices thing. Right? If you're doing that, you're still going to have request queues. Now, those request queues could grow unbounded, right? You could end up with infinite delay. You could end up with bottlenecks. And so you might want to use these types of mechanisms to figure out, okay, I need to maybe set up another worker when this queue fills up, okay? Or maybe I need to change the serving rate for my particular request queue, okay? Or I need to set up some rate limiting that propagates back to the source. Right? So these types of mechanisms may be too complicated for the internet, but there may be just a thing for balancing your microservices application. Right? And I think that wraps it up for today. Any questions?
Yeah, I was just kind of curious. I mean, this feels like you could be at risk, at high risk, especially when you're building more and more queues, to just basically make any low priority where it'll just never get served.
Mm-hmm.
Is there also like a timeout period in that queue where if it's been sitting in that queue for, like an hour and a half or I don't know, just some crazy amount of time where it just drops that whole queue then, like the low priority, or is that?
You could have it. You end up with an issue of starvation. Generally, the way this gets handled is that you don't admit any more packets to the queue. Now, weighted fair queuing is not going to cause starvation because every queue gets served, at least at some rate. If you have strict priority queuing, you could have starvation, where you never get to send anything from low priority. You could end up with packets that are quite old in these queues if they're not being sent, right? And so that could be an issue for some application where, if a packet arrives late, it's no longer useful. But then, maybe you should classify the traffic as higher priority if that's an issue. Or you could define a drop policy from a queue that says if a packet is old enough, we just drop it and let new packets be admitted to the queue. So your drop policy could be FIFO, it could be tail drop or drop tail, meaning don't add anybody else in, or it could be anything else, anything you want to do. Even though if you do something complicated, that's going to be more kind of computing involved in queue management.
Makes sense.
Mm-hmm. Questions? Anybody else?
So how is this better than the alternative? Because like the packets that make it into the queue with the token will get sent eventually, but the queue before, like waiting for tokens, like that queue still has like the same problems, right? Where that queue can fill up and packets will have to be dropped and stuff, right?
Yes.
Okay, so where's the advantage? Just the packets that do have a token will be sent eventually?
Yes. So the advantage is that down the road in the network, you don't have you're not sending more data than you want to, or than you configured, right?
Oh,
It's still
okay.
possible for the source to oversend, right? And that's up to the source to decide that it doesn't want to send, that it shouldn't send that much, but at least you're not congesting the network. Meaning that if you have a misbehaving source, well, then that source's packets are going to be dropped. Whereas if you just allowed every source to send data in the network, okay, queues are going to fill up eventually, but then all the sources are likely to be suffering from dropped packets, not just the one that's misbehaving.
Mm-hmm. Okay, that makes sense. Thank you.
Mm-hmm. Mm-hmm. Anything else? Anybody? All right. Well, thank you guys. Enjoy your weekend. I'll see you on Monday.
Everything.
Thank you.
Bye.